achieve the target reliability level subject to. Now this is what you minimize, and here is your constraint. And constraint is the total system failure rate you want less than or equal to so this is the target, and your total failure rate should be sorry about that. Your total failure rate should be less than or equal to the failure rate achieved should be less than or equal to the target failure rate, right? So here is your optimization problem. Okay. Now it turns out that in many cases, depending on the numerical values, you can actually come up with a closed form solution. Now sometimes some optimization problems you cannot solve. You basically have to plug in the numbers and then solve the optimization problem. But in this case, it is simple enough, you can solve it algebraically. Now there is a method called the Lagrange multiplier method. So let us use the Lagrange multiplier method. Okay, how many of you have seen that? I guess engineers should have seen it, or maybe have forgotten about it. In computer science, it's not quite that common because in computer science we don't tend to use that much mathematics. But depending on some of us, some computer scientists use quite a lot. So anyway, there is this Lagrange multiplier method, and we are going to actually skip it, but that's how I solved it. And using the Lagrange multiplier method, you can optimal failure rates. So I will tell you the optimal failure rates, and down here, optimal values of D. Okay, so the optimal failure rates. So the expression for lambda 1 is different, and that is equal to lambda sub st divided by f1 divided by summation of I equal to 1 to n beta 1I divided by sorry about that, beta 1 divided by beta 1I. So beta 1 is for module number 1. Now this is just the way iteratively the Lagrange multiplier method has been applied. And for lambda 2, for other lambdas, the formulas beta 1 f1 divided by beta 1 2 f2 lambda 1, and finally lambda n is equal to beta 1 f1 divided by beta 1n fn lambda 1. And the optimal testing time be given by, now the first expression turns out to be a little complex. Other expressions, so this is the expression for lambda 1, and this is for lambda 2 in terms of lambda 1, and this is for lambda n in terms of lambda 1. So d1 is given by 1 by. Now you might think that this looks like a complex mathematical expression, but it's fairly straightforward. You just set it up with whatever mathematics package you are using, plug in the numbers, and you have the answer. Okay, notice that assuming now this assumes that d sub I is greater than or equal to 0. In some cases, it may turn out that the optimal testing time for some modules will turn out to be negative. And that of course doesn't make sense, right? So you need to revise your numbers. So that means what will happen is that if you happen to have some modules with very low defect density relative to all others, then according to the optimization criteria, you shouldn't have tested them that much. But of course you can't go back. You can't put the bugs back in because you have already tested it. So anything that has been tested so thoroughly that the recommended testing time, if it turns out to be negative, you don't need to test them because they are already reliable enough. So it's the other modules that you need to work on to make them more reliable. Okay. In this paper, the font in some cases is a little too small. So I have to kind of, so sometimes I use multiple glasses. So these are my general purpose glasses. So I can see both distance and near, but it's not really optimal for near. And then I use a pair of glasses for the computer screen. And then if I have to read some reals fine, then I use a different pair of glasses. So each pair of glasses optimized for the specific reading task or viewing task rather. Okay. And d sub I is given in terms of so after I did this analysis, I noticed something that was both surprising and not unexpected. Okay, now let's look at some more. Now, did we say something about beta 1 before? Now we have earlier noticed, now as I was mentioning, we have done some work trying to figure out the meaning of specific parameters. So I remember that the value of parameter beta 1, remember the equation I gave? And you might remember that beta 1 is, or let's say beta 1I for module I would be, it is proportional to inverse of the software size. Remember that? We have talked about how to calculate the value of beta 1. And in the expression, the size is in the denominator. And, okay, what's the connection between the time, expected fraction of the time taken by a module when it is under execution and its size? What kind of relation you would expect? Any suggestions?
Say that again.
Can you say that again?
No. I asked, could you say that again?
Oh, so let's say you have modules of different sizes. And so f sub I is the fraction of the time module I is under execution. Now so what relationship would you assume between f sub I and its size, s sub I? Now it may depend on some specific situation, depending on the structure of the program. But let us assume that you didn't know much about the program. The default assumption would be that is proportional to software size. So if there's a bigger piece of code, it probably will spend more time under execution. So if you make this assumption, there is something interesting. Notice here, beta 11 F1, beta 1 to F2. So this factor would not depend on software size, right? And it does not depend on defect density. And here, this, they do not depend on software size. So notice, if that is the case, then for an optimal situation, the final optimized values of lambda for different modules would be equal. Does that make sense? Do you think that intuitively sounds like a reasonable thing? That you start with modules with different failure rates and you test them optimally. And according to this relationship, if you test them optimally, at the end they would have the same failure rate. Okay? And then there's another thing to observe here. And let's look at this here. Okay, let me ask this question. Let us assume that it's a new project and all the modules, they have the same defect density. Then what can you tell about the optimal testing time? They have the same defect density. Then you will notice that this will say that the optimal test time for each module would be proportional to the size. Beta 1 is inversely proportional to size, and it says that d sub I is equal to inverse of this. So it will turn out that in that case, if the modules have the same defect density, then the optimal testing time is proportional to the size of the module. Does that sound like a reasonable